So let's talk about our old friend, the array list. But before we get there, I want to tell you about a strange slide that I wrote last year. And I looked at it again, and I was like, oh, that's pretty fun. Let's do it. Okay, so let's imagine Grigameth. So Grigameth was this dog from the sorting lecture. You may remember him. He's sort of spooky, comes to you in your dreams, and you have bad dreams as a result. But let's say that Grigameth, he says to you, hey, I'll make a deal, mortal. I will allow you to appear to horses in their dreams, just as I've appeared in yours. And you can do whatever you want. You can ride the horse. You can befriend it. Whatever it is that you want to do with this horse in its dreams, it's great. But it's going to cost you. You're going to need to bring me hay. You're going to have to place it in an urn. And in fact, I'll give you two choices. This is, the kind, as a small person, right? There's a whole bunch of myth and folklore about little people trying to make deals with people to take their firstborn children. I don't know what it is, you have to guess my name, and otherwise your kid's mine. It resonates with me somehow culturally as a pretty short guy. So I love this urn stuff. That's my life. Anyway, so Grigameth says, first choice, I'm going to come to your house and eat 3 pieces of hay from your urn. From the urn. No. From the urn. And if it's not there, if there's no hay, you're in trouble. The second choice is that Grigameth will eat exponentially more hay over time, as follows. At the end of day 1, he eats 1 piece of hay. End of day 2, 2 additional pieces of hay for a total of 3 by that day. At the end of day 4, 4 additional pieces. At the end of day 8, 8 pieces, and so forth. So we'll say C sub I is the consumption of Grigameth on day I, and obviously it grows. So let's suppose that A sub I is the amount of hay we put in the urn to keep Grigameth satisfied. So for each choice, just ponder for a minute, what should A sub I be? How much hay do you need to put in the urn over time? Does it need to increase over time? What's a number that works? I'll give you guys a minute to ponder the deal with Grigameth. You can even decide which choice you like better, though that's not required. All right. So there's a number of different ways to ponder this little puzzle. It turns out that you can satisfy either of these requirements, whichever choice you pick, by just putting 3 pieces of hay in the urn every day. So the 2 choices are basically equivalent within a constant factor. It's actually a little cheaper to do choice 2, because if we look on any given day, the total amount of hay we need to have put in the urn by that day is about 2, right? So if you just come in and you put 3 pieces of hay every day, yes, Grigameth becomes ever more voracious, but he also arrives exponentially less often. So the exponentials cancel out, and so ultimately his consumption per day is effectively constant. Okay? It's a little different than that thing where it's like, I'll give you $1 today, $2 tomorrow, $4 the next day, and so forth. Because that's a really good deal. Like if the exponential growth happens at a linear rate, great, take that. Unless it's Grigameth who wants hay, then definitely don't take that choice. But here, if he arrives exponentially less often, it doesn't matter that his consumption grows. Now, what does this have to do with 61B? Well, it has a lot to do with array lists, Grigameth's data structure, I guess. All right. So I'll recall the A list we built in class. We had this issue, which was they get full. And you had a whole project where you talked about resizing. And our very naive solution in lecture was, well, let's just make the array 1 larger. We'll make a 1 larger array. We'll copy everything. We will set the pointer, or we'll put the last item in, we'll copy the pointer, and the old one gets garbage collected. Okay, that was our solution. Now, the bad side of this was what? Just slow. You're making all these arrays all day. It just seems messy. Okay, so that's not good. So this process of resizing up by 1, it's just extremely slow to do that for every single item. And in fact, we showed that the result of this would be that the operations would be linear time. Every time you insert into your array list, you have to make an entire new array. That's linear time. Every insertion gets bigger and bigger and bigger. Not so good. Now, we talked about how a better solution, the naive better solution is, let's just add 10 more or 100 more. But it turns out that that's going to be equally slow. And we're not going to analyze this in detail, like why this is bad. But we are going to talk about why geometric growth, very big difference, geometric growth here is going to be better. Okay, that is, we want to double our array size. Okay, so that's our that's how the ArrayList we implemented in Project 1 was, how the array stack in exam was, and how the list in Python is implemented. And so let's talk a little bit about why this works finally, now that we know a lot about asymptotics. Okay, and GigaMathCern is going to be pretty important. So the way resizes work, just intuitively, like an intuitive argument, and then you can maybe kind of pretend the lecture's over, but we're going to do a more intense version in a moment. But intuitively, we can imagine that as we resize, we need to make the array bigger to accommodate more stuff. And if we say when the array is full, we double it in size, what that means is that most add operations are going to be really quick. You're just going to throw stuff in the array until eventually sometimes you have a resize. But some of the insert operations are going to be expensive. Why are they expensive? Because you have to make a whole new array and resize. Because that's right. So like when we add, most adds, it's just item size equals x, size plus 1. That's super fast. But sometimes you have to resize. Now in the optional textbook for the rest of the course, which you don't need, but you can read, so the readings from next week on will be from this book, this figure shows you what is the cost of each insert into an array list. There's a slightly different context, but the figure still stands. And so we see that most of them, and we got to zoom in a lot here, they're all the same. This gray dots, that indicates that these are all the fast operations. These are the ones where you don't do any resizing. But occasionally you get these expensive ones where, okay, well this one costs 1, this one costs 2, 4, 8. Well, I'm off by a little bit because they started at size 8. But here, they have an operation that costs 64. You have to build 64 boxes or whatever their cost model is. And eventually, and over time, each of these expensive operations is double the cost of before, but they're also exponentially far away. Okay, so there we go. We're jumping away. All right. So what we could do intuitively here is look at this and say, well, I'm just going to take the total cost, right? I add 1 plus 2 plus 1 plus 1 plus 4 plus 1 plus 1 plus 1 plus 8, or whatever the values may be, and so forth. And I just divide that by how many items I have so far. And that's what this red line shows me. And we can see that the red does seem to increase, but it's increasing very slowly. Okay? So I can tell you two things. One, that the worst case is that it takes theta n time for a single insertion. And the average case, this is what we're going to be doing for the rest, is actually theta 1. So in other words, what I'm claiming about this red line is that it's converging to a constant. And here they've noted, for their example, it's 3. Right? You just put in 3. And so just like GigaMathCern, as long as you're basically thinking of it as 3 on average, you're good to go. If you bring 3 elements of hay to the urn every day, GigaMath won't consume your soul at night. Okay? Good. Okay. So that's the intuitive argument for why array lists, geometrically speaking, are good. We just appeal to GigaMath's tribute, GigaMath's urn. Okay? Now, probably if you are at a job interview and they ask you, let's say, or, I don't know, whatever, you're just trying to convince somebody that you know what you're talking about, and you say, well, it's just like that urn with the demon god with the hay, it's fine. They won't know what you're talking about, so let's talk about things in a slightly more rigorous way. Though I encourage you to try it and let me know how it goes. I think being yourself in all circumstances is a really lovely thing to do, by the way. I told this story very recently, hopefully not to anybody in this room, maybe, which was about how I did a scholarship application once where I included a picture of myself. This is a long story, so I'll do the very short version. But a picture of myself with my head through a cardboard cutout of a fetus. And then I just explained something about why it happened, and I received $2,000, even though the scholarship was for academic reasons. So anyway, be yourself. There's a longer version of that story. Come to office hours sometime. I'll tell you the whole one. All right, let's talk about amortized analysis, not in the context of demon gods who demand hay. Instead, what we're going to do is we're going to pick a cost model. That is, we're going to pick some operation that's going to act as a proxy for our array list insertion in terms of how much the time the computer is going to spend. We're then going to compute the amortized cost of the ith insertion. And then we're going to show that that cost is bounded above by a constant. So just like with Gigamet's earn, we're going to say the amount of hay we needed was bounded above by 3 per day. So in that sense, Gigamet's consumption is effectively constant. Same deal. Okay. So to get there, let me just give you a sense of what our cost model is going to be. So my cost model is going to be array accesses. Now you could pick something else, but that's what I'm going to pick. And it seems to track what's important. Remember the cost model, it's an arbitrary choice that we make up front. And we can make the wrong choice. It's totally possible. But in this case, I feel pretty good about this one. Okay. So let's think about the 5th insert into an array list. So we have 4 items. And then we want to add a 5th. Okay, well, there's no room for it. So what we need to do is make a new array of size 8. Right? That's one of the steps. I then need to copy 4 values into the new array. So I'm going to do 4 array reads. I read 0, and then I write 0. I read 1, I write 1. I read 2, I write 3. I read 3, I write 3. And so in total, I have those 4 reads I just mentioned, and those 4 writes I just mentioned. And then finally, we have one last write, which is, in this case, the value 4. So the total number of array accesses is 9. So for our purposes, I've decided that's the cost of this operation. That's just my cost model. Now maybe you say, Josh, why didn't you count the creation of the array? I don't know, it just seemed messy. Like, I don't know how, the array creation's kind of complicated. If you take 61C, you'll learn a little bit about that. So I just don't want to talk about it. You could also count, well, Josh, doesn't an array in Java actually have a bunch of default values? Shouldn't you be counting those array accesses? Yeah, you could count those too, but I'm just not going to. It's my cost model. And my argument for that is, these aren't going to be any different in terms of the orders of growth. That's what's really important, than this simpler cost model. But you can redo the analysis, taking into these into account, and you'll get the same result. Okay, but my cost model, to keep things really simple, because it's a lecture, reads and writes. That's it. Okay. Happy with that? All right. So here's the first 5 operations in my array list. And remember the goal here. We're trying to prove that array lists have effectively constant time. That's going to be our big goal. So let's say we have an array list of 0 with an array of size 1. The first write is, it's one operation. We put the 0 in there. Great. How about the next one? Okay. Is there room? No. So what do we got to do? Make a new array. So how many total operations is this going to cost us, do you think? 3. Yeah, we got to read, write, write. So we read the 0, write the 0, write the 1. 3 array operations. Okay, how about this one? Is there room? No, there's still no room. Dang, well, that sucks. Now what? How many array operations is this going to cost us? We got to copy, and then write. And so this copy, when I say copy, I mean read from the original array, write to the other one. And so the overall amount of information that we're going to have to, or operations is going to be read, write, write. So it's going to be 5 array operations. Okay, is there room now? Yeah, we finally have some room. Well, that's pretty good. I'm excited about that. So how many operations is this one going to cost? Okay, this is 1. So this is like the night when Gigamet doesn't come to eat the hay, but maybe somebody else has a little hay on the side. I have known occasionally, like I get hungry at night, just grab the hay I have set aside for Gigamet, just have a little munch. I figure Gigamet won't be so upset. Okay, so far it's been fine. All right, here we go. We got room now? Nope. All right, guess got to make another array. So these early operations are kind of expensive, right? we're getting Gigamet's arriving frequently. It's just like, come on, I'm like, leave me alone. Well, eventually he will, right? These resizes will become less and less frequent. So in this case, how many operations is this? 9. Okay, great. So that's 9. We end up with this array. The next one, that's only a write operation. That one's cheap again. Okay, any questions about that? That's what it looks like when an array list is running. Okay. So what I'm going to do now is fill in a little table that just summarizes everything that happens for a long time. And our goal is we're going to try and look at the amortized total cost, how much time it takes for our operations overall. Okay, so how we're going to do this is I'm going to fill in the top row. This is the cost of actually the W operation. So every single time I add, how many W's will there be? 1, always 1. So that row that's what that 1 means. It's saying there's always one new item I put. And the next one's going to be sort of the Gigamet cost. That's the resizing, okay? So when we do our first insert, there is no copying. So we say, no, there's no resize cost. Okay, whenever we get to 1, that's this array, this item, well, we have to do a copy operation. So I have a read and a write. And so I'm going to put the number 2 here to indicate that we had to make a new array and copy stuff into it. This one is the operation we just did. This is copy, or one of the operations we just did. We have copy, copy, write. So in this case, we have a total of 4 operations, which are involving reading and copying stuff over. So this one goes 4. Maybe you can see the pattern. Okay, finally, when we get to 3, that's this operation. We don't need to do any resizing, so there's no cost for resizing, no Grigameth to pay. How about here? What do you think is going to be here? 8, good. 0, 0, 0 here, 16. Great. Okay, so that's the cost of the resizing. And so the total cost will just be the sum of those. So this insertion takes 1 op, 3 op, 5, 1, 9, 1, 1, 1, 17. That's expensive, but okay. And so we look at this list, 1, 3, 5, 1, 9. Okay, so let's double check. 1, 3, 5, 1, 9. Okay, so we passed our unit test. Good. All right, cumulative cost. That's going to be the total amount of hay, so to speak, that Grigameth has eaten. Everything that's happened. So this will be 1, 4, 9, 10, 19, 20, 21, 22, 39, 40, 41, 42, 43, 44. I think that's right. Next slide will tell me. Okay, good. Ooh, and we can middle justify it. Good idea. Next slide. Okay, so we have just listed everything that this array list costs us. And so if we average this out, if we wanted to compute that red dot, so we go back to this figure from Sedgwick and Wayne's book. I want to figure out what this dot is so far. All right, it's kind of blurry. What do we need to do? Oops, got some more tables. Okay, oh, there. It showed for a second. So what do? If we want to estimate roughly on average how much things cost, be 44 over, I guess, 14. Is that what seems sensible? Yeah, 14, because there's 14 different operations starting with 0. And so overall, that ends up being 3.14 just by coincidence and not because I'm some huge nerd. I'm serious. I didn't do it on purpose. So anyway, I don't want you to think I'm sneaking pie jokes and everything, because that's just not my style. I'm more of a Grigameth demon urn guy and not like lame math puns. So we'll just live with it. All right. So that seems good. It seems like it's a small number, but I haven't really convinced ourselves. That's the verb-noun agreement error, but okay. We haven't really convinced ourselves that it's actually constant. Yeah, it's some small number, but maybe as n gets bigger, this keeps growing a little bit, over and over, more and more over time. So what I want to do is prove that while this number is interesting, it tells us roughly how much hay I need to bring out for Grigameth every day. We need to prove to ourselves that even if we keep going for years with this Grigameth thing, that it'll still be okay. All right, so that's going to be what we're going to do next. So any questions about the table, what we're doing so far? Yes. Still 3 times the number of items. So you're saying it feels linear rather than constant? Is that right? Oh, so it is actually constant. So the point here is that what you're noting is that the cumulative is linear in the number of operations, right? Just as in terms of like Grigameth's coming to the house and eating all the hay, his cumulative consumption was linear in the number of days, but per day it's constant. And here we're saying per operation it's constant. Yes, so every time I add one item, that single operation is on average constant. Okay, so the average cost of each insert is theta 1. Though it is the case that some of them are theta n. We can clearly see that, right? Some of the operations, when there's 8 items, it costs 17. When we get up to the next power of 2, it'll be 33, right? And so forth. But overall, we want it to feel constant. So I'll show you this is the last step for getting rigor out of it, which is I'm going to introduce a new term, okay? It's sometimes called the potential. This is kind of a wimpy version of this analysis. So if you go and take 170, they're going to define it in just a slightly different way where the A is on the left-hand side of this equals. But I find that for 61B purposes, I like this version better. Okay. So for operation I, the way this is going to go is we're going to choose an arbitrary amortized cost AI. So we're just making it up. That's going to be something we do, and that'll make sense in a moment, what I mean by that. And that cost that we choose, just totally arbitrarily, this is like us deciding how much hay to leave for Grigameth. I could just put 1 every day, and yes, he'll eventually arise from the ground and flames will shoot up and he'll eat my face or whatever. But I could choose to do 1. If I chose to do 4 or 7 or whatever, then I'd be in good shape. I could choose to do 1 on the first day and 1,000,000 on the second day. There's many different possible amortized costs that I would pick. Okay? And so that cost that I pick, it could be more or less than the actual cost for that particular operation. Now let's say that phi I is our potential at time I. You think of the potential as the cumulative difference between the arbitrary cost that you've picked and the actual cost. So you could think of it as how much hay is left in the urn at any given moment. So the hay on day 5 is going to be however much hay you had on day 4, plus however much you put in, minus however much Grigameth came and ate. And so if we select, and this is the key point where the math comes in, and it seems almost so subtle that it's pointless and silly, but and like trivial. But if we pick an AI, A sub I, such that phi I is never negative, then that's another way of saying the amortized cost, whatever we're providing as our amortized costs, it is an upper bound on the actual cost. This is just another wordier way of saying if you only put 3 things of hay in the bucket every day, in the urn every day, and Grigameth is always satisfied, you have upper bounded his consumption. That's all that sentence says, okay? But with just some like extra symbols that make it slightly more confusing. Now, using the example from earlier, Grigameth's choice 2, right? We can think of, so in this case, the actual consumption of Grigameth is the A right here. Oh, let's see. Did I mess this up? Actual cost. Yeah, okay, this is good. So the actual cost, the amount that Grigameth actually consumed was 1 on the first day, 2 on the second, 4 on the 4th day, 8 on the 8th day, and so forth. And the amortized cost, I just made it up. It's the amount I'm putting in the bucket was always 3. We can see that on some days I actually ended up with a gain in terms of the number of hay. What's a hay unit? Bales? No, it's a piece of hay. Okay, because then we're not moving whole hay bales. That's too heavy. So anyway, I'm putting in 3 this day, pieces of hay. Grigameth eats 1. There's 2 additional, and so forth. And the bottom line, the potential shows that on day whatever this is, we actually have 27 things of hay laying around, pieces of hay. Okay, so let's do it in the context of ArrayList if this table doesn't make sense. And I think once we do it interactively, it'll be more clear. Sometimes, by the way, people also think of the amortized cost as deposits, C's as withdrawals, okay, so consumptions by Grigameth, and this is phi as our total holdings. So again, we have our total cost of our operations. Actually, I'll copy it from the earlier slide, not the later one. So we have our total costs. Copy paste. Okay, okay. Nope. Okay. It's hard to do this because I always like to make sure I have the answers so we don't screw some up. Okay, here's our total costs that we computed earlier. And now we get to pick amortized costs. So we get to decide how many pieces of hay do we want to put in there. So I don't know, give me a number. How much hay do you want to put in the barrel the first day? Urn. 4. Okay. So let's just do 4 every day and see what happens. Maybe this is good, maybe it's not. So the question is, if we just arbitrarily decide to make this number 4, we just picked it, do we end up with a satisfied array list? It's our new Grigameth, okay? Well, what we're going to do is compute all of our changes in potential. Uh-oh, that's not good. Okay, okay, well, that one can be center just. Okay, that's fine. All right, on this day, we put 4 pieces of hay in the urn. The array list wanted only 1, so we have 3 more potential units. So our total potential is now 3. Okay, how about on this day? Then what? 1, right? We actually end up ahead. We put 4 in the bucket. We ate 3, so we end up with 4. Okay, how about here? Amortized. We decided to only put in 4. The array list wanted 5, so we end up with -1. But we have plenty in the bank to cover that, right? Just like if I put 3 pieces of hay in the bucket every day, the urn, sorry, it's very important. Grigameth's not going to eat out of some bucket. You put a little more hay in each day so that when the reaper comes, there's plenty to satisfy him. Okay. So next up here, the answer, what's the change of potential? 3, so we get up to 6. All right, this is a costly day. So in this case, we actually need to spend 5, but we still end up ahead. So that's 1. Okay, so we got 3, 3, 3, so we get up to 4, 7, 10, and then on this day, what happens? -13. Oh no, a problem has arisen. We've gone negative. So our potential went negative. Now our goal was that the potential should always be greater than or equal to 0, and I didn't actually say this out loud, but we also wanted our amortized cost to be something that's just a constant. I didn't want this to grow. I mean, I can cheat. I could just say, well, the amortized cost is like 1, 3, 5, 1, 9, 1, 1, 17, and so forth, and that will obviously satisfy the array list. But that doesn't tell us anything. So what I want to do instead of 4, I don't know, we need to pick a bigger number. So someone pick a bigger number. 5. All right. Okay. So 5. Okay, we're going to do a little number magic. Okay, so if we do 5, and let's see if we can get through this quickly. I'll see. So if we do 5, I guess, come on, delete those. Go away. Yes, all right. So on this day, we end up with a surplus of 4, 4. Here we end up with a deficit. Oh, we have a 2. Okay, good. We're ahead. 6. All right, we are exactly good, so we stay at 6. Here we're at 4, so we got 10. We got -4, so we're at 6. And now we're at 4, 4, 4. We get to store up a lot, 10, 14, 18. Then we get to this day, minus 12? Yes. Plenty. Got a lot in the bank. So we got 6. And we continue on. And obviously, we're not going to go negative in potential. Now, does 5 work? I'm 99% sure. And if we were to do a fully 100% rigorous 170 proof, you could sit down and say, look, surely it is so. You could write out some sums. And you could demonstrate that that potential here is always positive. By doing that, you have proven that the average is constant. Now, this is actually a pretty technical thing, and I'd say that most data structure classes probably don't touch this at the sophomore level. And we're not going to go super deep on this. I'm not going to have super crazy. I mean, like, it might appear as one of those sort of pushing you to the limit midterm questions, but this is not a core topic of 61B. But I hope you found that the approach to be an intriguing way to try and assess the runtime of a function, right? So on average, what we can say is each operation takes constant time, and therefore arrays make good lists. But if you wanted to be super rigorous to the 170 level, you'd need to think very carefully about proving that this number is always positive, okay? So to summarize what we got, big O and big omega, they're a lot like big theta, they just work slightly differently. The number one thing I want to mention right now so that you don't get this burned into your brain early, big O does not mean worst case, and what does that mean? Big omega does not mean best case. All right. And then the other part we got amortized analysis. I hope you found it an interesting way to approach problems. And if you take 170, you'll see that in more depth. All right. Thank you, everybody. Next week, we'll start with data structures. Good luck with Project 2. Start studying for that exam once you're done.